Rotations are something that almost everyone in Blender does. However, if you actually understand what's happening behind the curtains, you could save hundreds of hours preventing different problems you might face like gimbal locking or unnecessary rotations. Just like how, instead of rotating about the y-axis by 90 degrees, it does this super weird rotation to get the exact same, which could have been done by just rotating about the y-axis. As you can see, it was the same as just rotating about the y-axis by 180 degrees. However, it caused that weird rotation instead when it was keyframed. So situations like this come up quite often, and it ends up taking a lot of time to just debug. Instead, if you truly understand how rotations work internally to Blender and what all of these various rotation modes are, you could avoid all of this and save yourself hundreds of hours in the long run. So in today's video, we're going to actually demystify what all of these rotations are, why they're used, and when to use them as well. It's going to be super useful and it's going to get slowly math heavy towards the end, but I'm going to keep it super intuitive so that everyone can understand. So I suggest watching till the end, and until we get to there, let's go ahead and first understand what the difference between local and global rotations are. Essentially, you can transform an object using its local axes or the global axes, and that can be controlled via these transform orientations. So if you see what the global axes are, they are the axis of the world. So this red, green, and blue axes of the entire world frame. So if I was to rotate this about the global y-axis and then choose to rotate about the global z-axis, you see how it's rotating about the z-axis of the world and not its actual z-axis. However, if I change this to local, then you can see if I rotate about the z now, it rotates about the local z-axis and no longer the world z-axis. So that's something that you really need to understand before we go further into this. But essentially, rotation can either be on the local axis or it can be on the global axis, just like this. And once we understood that, we can go ahead and first talk about the different types of rotation modes present in Blender. So rotations in Blender are of 3 different types, or at least they're computed in 3 different ways. The first method are called Euler angles, or Euler rotations. These by themselves have 6 different modes, and those are XYZ, XZY, YXZ, YZX, ZXY, and ZYX. And the default rotation within Blender is the XYZ Euler rotation. We'll talk about what each of these are in a second, but before that, we'll say that the other 2 types of rotations are axis angles, which takes in 4 inputs, X, Y, Z, as well as W. And then we have Quaternions. Quaternions is the most used in the back end of Blender, but is rarely used by us manually. However, it's super useful if you actually know what it does, and it's very interesting as well, so we will touch upon it. Quaternions also take in 4 different values, W, X, Y, Z, but they're completely different from the axis angle. And now that we understand what the different types of rotations are in Blender, we can go ahead and start understanding what exactly Euler XYZ rotation means. Remember, as I stated, that rotations can happen on the local or global frames. Whenever you change these angles using Euler rotations, they're going to be rotating about the global axes, but in a specific order. So XYZ means Blender is going to compute this rotation as first rotating by -45 on the X, and then 43 on the Y, and then 12.15 on the Z. So it's going in that specific order, and the order definitely matters. Let's take an example to showcase the fact that the order of rotations matter. For example, if we rotate about the X by, let's say, 75 degrees, and then we rotate about the Y by 170 degrees, and then maybe we'll rotate about the Z-axis by 80 degrees. So let's see what that looks like on this particular cube. So first we rotate on the X-axis by 75 degrees, then rotate on the Y-axis by 170 degrees, and then rotate on the Z-axis by 80 degrees. This is now the orientation of the cube. Let's do the exact same thing on this cube, except let's change the order. Let's do Y first, then X, and then Z. So if we rotate about the Y-axis by 170 degrees, and then rotate on the X-axis by 75 degrees, and then rotate on the Z-axis by 80 degrees, you see we get completely different orientations for both of them. In this case, the blue is literally pointing in this particular direction towards the left, and here the blue is pointing towards the right. Now, I already recorded this once, but I did make a mistake, so let's go back to the original video. So the order of operation definitely matters. In fact, if we were to take this and have the exact same rotations, but just change the order in which we're doing this, so instead of x, y, z, we do x, z, y, you see it does cause some sort of a change. And changing these modes changes the final look of this because it's changing the order in which it's doing this, which as we saw does change the final way in which this is going to rotate. So because the order matters, it actually becomes a lot easier to visualize this only when we're going about in that order. A rotation about x does the global x, a rotation about y does the global y, and a rotation about z does the global z. However, if you try changing the order in which you're placing these, it's no longer going to look that obvious. So if you see, right now I have the rotation about the z at some arbitrary angle. If I was to change y now, it's no longer going to be rotating about the global y-axis anymore. Let's take a look at that. You see now it's not rotating about the y-axis. In fact, it appears to be rotating about some axis that's probably something like this. So if we take a look at the rotation, it's moving about that new axis, which is not the global y-axis. It's clearly not. And that's because we had a rotation on the z before the rotation of the y. So that's why it sometimes becomes counterintuitive. Instead, if you wanted to have the z-axis rotation done before the y-axis rotation, you would have to change this Euler angle order to be maybe x, z, y. So that way you could set the z rotation to whatever you wanted before you play around with the y. So now it's going to rotate about the z to whatever angle you want, and then you can rotate about the global y-axis after setting whatever you wanted the z-axis rotation to be. So that's why these modes actually matter, and it can speed up your workflow so much if you understand it. But of course, that's not all there is to know about these Euler axes. The main issue with Euler axes is it causes something called gimbal locking. And you can see it gives a warning itself saying that it's prone to gimbal lock. And gimbal locking occurs when you suddenly lose 1 degree of freedom while trying to rotate. And this gimbal locking occurs quite often when you're doing things like trying to rotate via geometry nodes using maybe the transformation matrix. So if you search for a transform geometry, you see it has rotations x, y, z, and sometimes you'd want to rotate using these. Now by default, even this rotation is using Euler x, y, z. So it's the same as the default x, y, z. But sometimes you want to get a very specific rotation, and that might start with a rotation about the y-axis by 90 degrees. And then you say, okay, now I need it to just rotate a little bit about this x-axis. So you try rotating about the x and you see, okay, that's not the correct axis. And then you try rotating about the z and you see it's rotating about the exact same axis as the x. So no matter whether you change this x or the z, you just lose that degree of freedom and now you can no longer rotate it about that axis. So this is called gimbal lock. You've just lost 1 degree of freedom because y is 90. And sometimes animators struggle for hours together trying to figure out how they can go ahead and just rotate this about the x-axis. And they might come up with various different hacks like parenting this to an empty and then rotating the empty and things like that. Whereas a simple solution would be just to change the mode of operation to essentially have y first and then the others. That way, if you have this set to y first, you can now rotate this to 90 degrees. And then you have rotation about the x also free, and you have rotation about the z also free, so that you can do whichever one you wanted. And that is the power of switching these different modes. And now another thing to talk about these XYZ rotations is we spoke about how it's like it's a global transformation when you do it in the correct order. However, if you do it in the reverse order of whatever the mode is set to, it becomes essentially the exact same as local transformations. So if instead of going XYZ, you go about it in ZYX, it'll be rotating about the local axes. So as you can see, if I rotate about the Z, it's moving along the local Z axis, which is currently the global Z axis itself. But then rotating about the Y is rotating it about the local Y now. And then rotating about the X is going to rotate it about the local X axis. So that's something that's also really cool. How if you were to rotate X, Y, and then Z, it's going to rotate about the global axes. But if you rotate it in the exact opposite order, Z, Y, and X, it's then going to be rotating about the local axes. But remember, all of this is only easy when it starts off as 0, 0, 0, because that way it matches the exact local transformations. But if it's starting off in some other arbitrary random thing, now if I choose to rotate about the X, it's not going to be the global axis at all because it's already rotated and X at the end is the local X axis. But if I rotate about the Z, you see it's going about the global Z axis. So here it's the local X and here it's the global Z. So that kind of gives you an idea of why gimbal locking occurs. Because if this middle angle becomes 90 degrees, then rotating about the z should be rotating it about the global z-axis, which is the local x-axis. And this x is going to rotate it about the local x, which is the global z. And that's why we lost one entire degree of freedom. So you tend to reach these because of the way how the rotations are actually calculated. And it's calculated using rotation matrices or transformation matrices. If you want to know more about transformation matrices, you can check out the matrix demystifying video that I have over here that goes into depth about matrix transformations, why they're used, where they're used, and how to use them within Blender's new geometry nodes. But essentially, the rotations are calculated using sine and cos, and the inverse of those matrices are calculated to determine where each of these positions go. And the inverse involves dividing it by the determinant. And because this is sine and cos, when you have something like 90 degrees, cos of 90 is 0, and dividing it by 0 is essentially undefined. So that's why you can't quite get a perfect solution, and it requires a very sudden change. So now let's talk about a practical situation where this gimbal locking causes an issue. And that could be when, suppose you're in a camera view and you've used a track to constraint to lock the camera to the particular cube. So now the camera is always looking at this cube. If I was to just take this camera and try moving it along the y-axis, you see it's still looking at the cube, it's looking at the cube, but then just as you cross by, it just starts spazzing out and something weird happens. And that is happening because we reach that gimbal lock situation where the rotation essentially becomes 90 degrees and we lose that degree of freedom. So if you were to go ahead and just keyframe this and you play this animation, you'll see there's a sudden area where it flips by 180 degrees. And that flip happens literally over like 1 or 2 frames, which is not something that you would want within an animation. It's so abrupt and it's definitely not a nice, smooth rotation. And that's because this track to constraint, the way it's rotating this is again internally using Euler rotations. So ideally, instead of doing this, you would always want to have this go around the object rather than just over the object, so that it prevents that direct 90 degrees and it rotates from around it and comes down. So that is what you would need to do, because if you try going straight up, there's going to be a sudden flip, which is not something that you want. You do not want this sudden flip. And I personally don't know how you can do that for the track to constraint, but if you are manually keyframing rotations, you can simply change the mode to a different mode to prevent that. And now let's talk about another problem that sometimes occurs with this particular mode of rotation. And that's the fact that you could have the exact same rotation via different values over here. So if you see, this rotation is simply a rotation about the y-axis by 180 degrees. But you can get that exact same rotation by first rotating about the x by 180 degrees and then rotating about the z by 180 degrees. That gives us the exact same orientation as just a rotation about the y by 180 degrees. Now, in this very simple situation, it's easy to see that, okay, it's the exact same as just a rotation about the y. But often in more complex animations, maybe like this animation where you're animating a cube, you don't have the freedom to choose the axes just like that, and you have to see what makes the most sense for your situation. And if you haven't seen how to animate this particular Rubik's Cube, you can check out this tutorial over here, where we go step by step on how to animate a Rubik's Cube just like this. And even there, it's very important to choose the correct mode of rotations, and we'll get to that in just a second. But essentially, if you were to keyframe this and then go over to another frame and just rotate it, and let's say you don't really know what axis you're rotating by, but you know the final position has to look essentially like this. So you take it to this position and then you tap I, you would expect it to just rotate about the y-axis. But instead, it does this weird rotation where it goes in various other axes as well and orientations to finally reach that final position. Whereas it would have just been much simpler to have rotated it about just the y-axis. So here you can see the two rotations side by side, where one is just rotating about the y-axis and the other one does all of that other rotation to finally end up in the exact same position, but it does a lot of weirder rotations as well. So those are things that you might have to take into consideration when animating for XYZ Euler or any Euler angles as well. And that finally brings us to the next type of rotation that's available within Blender, which is the axis angle rotation. So if you change this to axis angle, you see it has W, X, Y, Z, but the X, Y, Z are essentially values, whereas the W is in degrees. So this determines a vector which is going to be the axis about which we can rotate. So if this axis is 0, 0, 0, this rotation does nothing. But we can clearly choose one axis. So let's say we want to rotate about the y-axis. We can change this to a y value of 1. And now if we rotate, it rotates just about the y-axis. Similarly, if you were to go ahead and choose the x-axis, so let's change the x-axis to a value of 1, it will rotate about the x-axis. Now, if the other values are 0, remember it doesn't matter whether this is 1 or it's something like 0.1, it's still going to do the exact same rotations. So 0 to 90 and so on and so forth is still going to happen. But it does matter if this is positive or negative, because if this is -1, in that case, you see the rotation was in the opposite direction. So now a better way to view this would be from this particular perspective. If the x-axis value was +1, then as we rotate, this object rotates counterclockwise. So you can see with a value of +1, as we move the w in a positive direction, it rotates counterclockwise. However, if you were to change this to a value of -1, if we were to start rotating this, it starts rotating in the clockwise direction. So essentially the direction of rotation flips if we change this from positive to negative. Now that's well and good for if we just choose x or y or z. But what happens if we start putting values in between these? So what's happening is we're actually determining the axis around which it's going to rotate. So if we were to change x to 1 and y to 1, the vector that we are creating is essentially 1 unit on the x-axis and 1 unit on the y-axis. So it is right here, and this is the vector that we created, or the axis of rotation. So if we were to go ahead and now rotate, you'll see it rotates about that particular axis. So if we were to align our view to that axis, so something like this, we would see that the rotation looks like it's rotating exactly about that. So I think that should help you make more sense out of it, but it gets even more interesting. Suppose instead of just having it as 1 and 1, we had it at 2 times for x and 1 time for y. In that case, the new vector is no longer here, but it is at 2 times of x. So this is 1 and this is 2. So it's over here, but y is still 1. So the new vector is here. So this is going to be the axis of rotation, and no longer is it going to be this. So because this is now the new axis of rotation, as you see, if we try to align it to our previous axis, it will not seem like it's rotating about that anymore. It seems to be rotating about a different point. So if we align it to the new vector, so now our view is perfectly aligned to the new vector, you can see that it seems to be rotating about that point. So that is how we determine what these values should be. Now it gets even better. As you see, if we were to now increase this value to a value of 3, it would essentially go up to here, and this would be the axis of rotation. Similarly, as you slowly try increasing that greater and greater, it keeps moving more towards the x-axis, and it keeps getting closer and closer to the x-axis until eventually at infinity it becomes the x-axis. So even though this is 1, if we change this to a very high number, this rotation will seem like it's rotating perfectly about the x-axis. But remember, these are again relative. Now if I was to go ahead and change this y-axis to a value even greater, let's go with 6,000 or 60,000. Now it's so much greater than the x, it'll seem like it's moving about the y. So that's essentially what these values do, and it's pretty cool. Because, for example, if I wanted to rotate it perfectly about this particular corner, it would have been extremely hard to do if I was trying to use Euler axes. So if I was to try to change this to XYZ Euler, I could maybe try to align the view and then get it to just rotate. But again, you see how that's not that easy to do, but it becomes a lot easier if we just change this to axis angle, choose the axis as x value of 1, y value of 1, and z value of 1, and then we rotate, and it rotates perfectly about that corner. So that's the power of axis angle and how you can use it in various situations. Now you see why this becomes very hard when you're trying to use Euler angles is, imagine you take this and you align an empty perfectly around the axis that you did want to rotate it about. And then you try parenting this to this empty, and now you select this empty, you add in a keyframe, and then at around frame 120, you rotate about the local y-axis, which is the exact axis that you wanted to rotate by. So you see it's rotating perfectly exactly as you wanted. So now you go ahead and make it like 180 degrees, and then you tap I. And because you just rotated about the y-axis or the local y-axis, and you think that, okay, this looks really good, you try to play the animation and you see it is not at all doing what you expected, and it's not rotating about that point. That entire point is rotating all the way around. So clearly there is something wrong. And essentially, that's why it's so much harder to get these rotations using Euler angles, and it becomes a lot easier using axis angle rotations. But this finally brings us to the final type of rotations, which are quaternions. By default, quaternions look like axis angles because, again, it's w, x, y, z. But now you see the w is no longer in degrees, but it's just a value. So this quaternion is actually a 4-dimensional vector. So now we're going to get into the math heavy section of this video, but don't worry, we're going to keep it super simple and intuitive for everyone to understand, even if you absolutely despise math and haven't done higher levels of math or high school math. Essentially, to understand quaternions, we need to understand two things: complex numbers and vectors. So I'm sure everybody knows about vectors because we already did a Demystifying the Vector Math Node video. Definitely check this video out if you haven't already. But essentially, vectors are in 3 dimensions and are depicted using 3 values, x, y, and z. But a quaternion is essentially like a 4-dimensional vector. So it's the exact same thing as a vector, except it's in 4 dimensions. So instead of just having x, y, and z, it has a w, x, y, and z. And that can be plotted in a 4-dimensional graph, which has the normal x, y, z coordinates, but also a 4th coordinate that is perpendicular to all 3 of these, which cannot be visualized because we only have 3 dimensions here. But essentially, that's going to be a 4th dimension that is perpendicular to all of these. Now, it's really hard to visualize, but mathematically, it works out. But it's not as simple as this, because quaternions usually use complex numbers. And that is what I'm going to touch upon right now, but I'll try to keep it as simple as possible. To understand complex numbers, you need to understand square roots. And I'm sure everybody knows what square roots are. For example, the square root of 4 is equal to plus or minus 2. Technically, it's only plus 2 because of surds, but if you think about it, we can get 4 by multiplying 2 into 2, or by multiplying minus 2 into minus 2, and that's also equal to plus 4. However, if you wanted to find something like the square root of minus 4, we possibly couldn't, because even negative 2 into negative 2 is only equal to plus 4. Any number into itself is always going to be positive. So how do we get the square root of minus 4? And that's when mathematicians invented a new method of doing this by introducing something called iota, which is represented as I, and essentially it is an imaginary number. So they've gone ahead and used a property of square roots where you can split the square root. So for example, the square root of 16 can be written as the square root of 4 times 4, and that can be split into the square root of 4 times the square root of 4, which would mean it would be 2 into 2, which is equal to 4. So that's how the square root of 16 is equal to 4. Similarly, what they've done is if you had the square root of minus 4, they would write this as the square root of 4 times minus 1. And what scientists did is then defined this I to be equal to the square root of minus 1. So that way we get the square root of 4 times I, which implies it's equal to 2I. So this 2I is a purely imaginary number. And similarly, you could have various other imaginary numbers like 5I or so on and so forth. But this now brings us to complex numbers. So complex numbers are essentially real numbers plus imaginary parts of the real number. So an example could be 3 plus 2I. This together is a complex number. And so mathematicians represent this on something called the Argand plane, where you have a real axis and you have an imaginary axis. So if you were to represent 3 plus 2I, it would be 3 units on the real axis and 2 units on the imaginary axis. So 3, 2. This point, which is essentially like a vector in 2-dimensional space, would be 3 plus 2I. And now the cool thing is, other than this representation, you could also represent this as some value r and an angle theta. So that would be the polar coordinates. So it could be represented as 3, 2, or it could be represented as that radius and the angle. And the cool use of this is that if you were to now rotate this, you could simply multiply this by another imaginary number to get some form of rotation. To give you an intuition, if you want to rotate any imaginary number on this plane by 90 degrees, you can simply multiply by a value of I. So multiplication by a value of I would imply 3 times I, which is 3I, plus 2 times I times I. Now I into I, remember I is the square root of minus 1. So if you were to square I, you would get a value of minus 1. So So that means this becomes -1, and 2 into -1 is -2. So that way you get -2 plus 3i, because you always try to write the real part first and then the imaginary part, which is the convention of x comma y. So that's why -2 comma 3. So let's go to -2 and then plus 3. So this particular point, if you were to rotate this vector, it would come to this exact point. And this, which is -2 plus 3i, is essentially this vector rotated by exactly 90 degrees. So I hope that made sense. You can create rotations about one specific axis by multiplying by an imaginary number. Now, quaternions take this exact idea and expand it to 3 dimensions of imaginary axes. So for a quaternion, you have 3 imaginary axes, one for the x, one for the y, and one for the z. So remember, we were representing this imaginary axis by I. So here you would have I, but this is also imaginary. So this is going to be represented by j, and this is going to be represented by k, where all 3 of these axes are imaginary. And then you have the 4th axis, which is perpendicular to all of these, which again, we cannot visualize, which is going to be the real part, which is going to just be w. Now, if we were to multiply any point with this set of imaginary or complex numbers in this 4-dimensional space, you could get a 3-dimensional rotation. If you think about this, we were able to get one value of theta, or rotation by theta, by using a 2-dimensional plane. Since we're in 3 dimensions, if you see for any of these, we would have to have one rotation about the x, one about the y, and one about the z. So because 2 dimensions gave us one value of theta, if we go up to 4 dimensions, we get all 3 values of theta. So hopefully that is the intuition that's good enough to appreciate quaternions, because we needed 3 dimensions of rotations in 3D space. So we're using a 4D space that we can simply multiply values by to get 3 unique theta values or a rotation about the x, y, and z. Now what this w, x, y, z does in the quaternions is determines or decides what this value is that we're multiplying it by to get the appropriate rotations. Now, of course, calculating what the x, y, z rotations should be requires a lot of math, but luckily Blender does all of that math in the backend and we don't necessarily have to worry about it. If you are interested in computer graphics, you will definitely get into the math. But for most of us 3D artists, we don't need to know it. But hopefully this gave you an understanding of what's happening, but you still don't know why we would ever use that when we could have just done it using axis angle or Euler rotations. And the reason why we use quaternions is because it gives you the most efficient rotation every single time. If we set this mode to quaternions, you can now have whatever crazy rotation you want, and when you keyframe it, it will get the most efficient rotation to reach there. So let's give you the exact same rotation, or the exact same example. If I was to do Rx 180 and then Ry or Rz 180 and then tap I, so that we now have the rotation about the y-axis by 180 degrees, you see the quaternion determines that the y-axis is the axis for the most efficient rotation. So this does something very similar to axis angle rotation. In fact, it is the exact same as axis angle rotation, except when we had it as axis angle, we had to choose the axis by ourselves, which as you saw was not really convenient unless we knew what the exact vector was. But in situations where we don't know what the exact vector is around which we want to rotate, it becomes very hard to use axis angle. Instead, quaternion will always determine what the best axis is to rotate about and then rotate about that axis. And that is why we use quaternion rotations. Another quick note is that Blender uses quaternions for things like inverse kinematics because quaternions does not undergo the gimbal lock problem. So there are no gimbal locking issues when using quaternion rotations. And that's why whenever you're doing things like inverse kinematics, generally the solutions are always done via quaternions. So that is another use case of quaternions, which we don't generally do face to face or manually, but Blender takes care of it internally all the time. Again, if you were trying to follow along the Rubik's Cube tutorial and you did not switch this to quaternion, you would have seen that the sides rotate in crazy ways. But all of that is prevented by using quaternions because that gives us the most efficient rotation without having to worry about which axis it's going to be rotating about or any of that. And this was an extreme example, but let's just take another example to drive home the fact. So let's say we do this, we go over to frame 120 and then just rotate it by some amount, let's say this, and then tap I. Now you see it gives the most efficient way to reach that specific orientation. It essentially finds the correct axis angle and then rotates about that. But let's now add in another cube and just copy the rotation and then apply it. Now let's tap I, go back to frame 0 and then Alt R and I. Now with XYZ Euler, we have the first and the last frame as the exact same rotation. But let's see what happens in between. So the axis angle clearly takes the simplest rotation, but XYZ Euler does a little bit of a different rotation, and it does a lot of extra rotations to reach that same position. So that is what I am trying to show. It's, I think, a little harder to see, but if you look at it, you see how the two essentially diverge and then converge over here, with the axis or the Euler rotations going a lot longer and taking a much rounder approach to reach the exact same position. And we can try the exact same thing with axis angle as well. Now you see all three of them have completely different rotations, even though the first and last frames that we keyframed is the exact same. Quaternion gives the most efficient, and axis angle in this situation has the most random rotation because we aren't defining an axis that it should be rotating about, and hence that axis is changing over time. As you can see, the values for the axis itself is changing. So even though these are completely the exact same rotations, just by changing the mode, we're getting completely different results. And now I hope you understand why we would use each of them. Another thing that you need to note is that if you were to ever change the mode, all of your keyframes in the rotation does get removed. So you will have to add in keyframes again for the new rotations. But with that, I think you should get an understanding of what these different rotation modes were and why they were used in different situations, when to use them, when not to, and why they make life so much easier. I will have a lot more of these tutorials coming out where I demystify the fundamental concepts that run Blender. So if you're interested in those, definitely subscribe down below and let me know what concept you would want demystified next. So until the next video comes out, thank you so much for watching. Keep creating and don't forget to stay creative.